Right, we've got P2 topic, and you can't see that, P2 topic 4. This topic is follow on from topic 3, clearly, and we are looking here at sections called vehicle forces and momentum, and another section called work and energy. So I'm just going to put the tracker to one side and see what I can talk about for a few minutes that might help you in terms of last minute revision in preparing for your P2 exams. So first of all, really easy. We've got a person in a car here, and here we've got a 3-year-old girl with an ice cream cone, not paying any attention to the road because she's got an ice cream cone. That's all she cares about in the world. Now this driver needs to first spot the hazard. At the moment, this driver spots the hazard and sees the little girl who's actually walking in the middle of the road. Then you begin to think, oh dear, what shall I do? The thinking time begins. And hopefully your brain will tell you to put the foot on the brake and stop the car so you don't have 3-year-old girl spilt all over the road. So we have thinking and braking, and hopefully that will result in stopping. And then all we need to do is add some distances, because the time it takes you to think, the car will be travelling a distance, and then you put the brakes on and the car won't stop straight away. It will take some time. Together these two things add up to the stopping distance. What you need to think about though is the factors that might affect these things. So think about the mass. If the vehicle is heavy, if it's carrying passengers, if it's carrying luggage, if it's a big 4x4, if it's a truck or a bus, if it's got big mass, it's going to take longer to slow down. The thinking distance is unaffected, but the braking distance will go up. If the car is travelling fast, then the thinking distance is increased because the car will travel further in a given time, and also the braking distance will increase because the car is travelling faster and therefore will take longer to stop. The stopping distance will increase because both of these increase. The driver's reaction time will only affect the thinking distance. What will affect the thinking distance? Well, it might depend on being ageist, the age of the person, because when you're young, fit and healthy, you have better reaction times. It depends whether you've been on drugs, and you might have been on drugs that speed up your reaction time, like cocaine, amphetamines, or maybe drugs which slow down the reaction time, such as alcohol, which is a depressant. Certainly, it's a big problem. Drink driving causes a lot of accidents even now still. Because not only does it slow down your thinking time, but your judgments, your ability to make judgments, your sense of space and coordination, all affected. So the state of the driver's mind and body is also a factor. Even things like being tired can affect you. What can affect the braking distance? Well, we're talking about the state of the road, really, and the state of the tyres. Do they have a firm grip on them? Have they been well maintained, the brakes, that kind of thing. And there may be some other things that are a factor, such as weather, if it's been raining or if it's foggy. Certainly if there's ice on the road, that will change the braking distance. So quite a few factors involved with that. This vehicle has got mass and it's got a speed. The speed is in a straight line, so we could call that velocity because it's traveling in a straight line. If we consider that this vehicle is traveling in a straight line, we can say it's got momentum. Momentum is a measure of mass multiplied by velocity, and mass is measured in kilograms, velocity is measured in meters per second. Momentum does not have its own units. It's measured in kilogram, dot, meter, per second. Mass is a scalar. It doesn't have direction, it just has size. Velocity is a vector, it's got direction. So if the velocity is in that direction, the momentum must also be a vector. It must be given in a certain direction. And so you may have to work out momentum. If you have to work it out and give an answer, think about the units. You must also give a direction. Now the question is, we need to talk about the conservation of momentum. So I'm just going to finish part one by thinking about the conservation of momentum. If we think about this car, and let's say this car has got a mass of 1,000 kilograms, and let's say it's got a velocity of 8 meters per second, and it's obviously traveling in that direction. So if we work out the momentum of that car, the momentum is equal to the mass, which is 1,000 kilograms, multiplied by the velocity 8 in that direction. So the total momentum is 8,000 kilogram meters per second in that direction. That is the momentum before the car hits the little 3-year-old girl with an ice cream cone. Now let's say she weighs only 50 kilograms, and at the moment she's not moving at all. She's stood still staring at her ice cream in a world of her own. So she's got zero momentum. If we look at her momentum before the collision, excuse me, that's a school bell. The momentum before the collision is 0. We could calculate that because we've got the mass, which is 50, multiplied by velocity 0 kilogram meters per second. It's got no direction or size. So this is the momentum before the collision. Now what the conservation of momentum says is that this stays the same. So this will be the same after the collision as well. Now if the car stops after the collision, then the momentum of the car after the collision will be 0 because its velocity is 0. It's got a mass of 1,000 kilograms. Multiply those two together, you get 0 kilogram meters per second. So the momentum of the car, if it stops after the collision, is 0. So where has this momentum gone? The total momentum must remain the same. The conservation of momentum states that the momentum before a collision is the same after the collision. So where has it gone? There's only one place it can go, the little girl. So we have now got 8,000 kilogram meters per second in that direction. That's the momentum. This little girl has got a mass of 50 kilograms, and we need to know how fast she is moving. If we take that and divide both sides by 50, we end up with 160 in that direction meters per second. That is how fast the girl is moving. She flies across the road, and she's going to travel 160 meters in just 1 second. She doesn't stand a chance, does she? But you might have to calculate some of those sums. And if you buy an ice cream, do be aware of things around you. Thank you.